Hello everyone. This is Zhuoqun, and today I will presentation this paper called "The Neural Hawks Process: Narrowly Self-Modulating Multivariate Point Process." And this will I will from 4 parts to introduce this paper. First is the introduction, and the second is the model, and the experiments finally will be the conclusion. First, in our daily life, there are many event sequence, and such as the medical events, consumer behavior, social media actions, and other event streams arising news, animal behaviors, and music. For example, the consumer behavior. Each online consumer can have a sequence of online interactions. By modeling these distributions of this sequence, we can learn their purchasing patterns. This is very useful for recommending the new product. And so this sequence, many events in the world. So in general, many events in the world are correlated, and a single event or a pattern of events may help to cause or prevent the future events. The ability to find correlations among events is very important problem, and it will be very useful to predict their future events. For example, predict the most desirable activity at a given time t for a user, or predict the returning time to a particular activity for a user. That means which events are likely to happen next or when they will happen. In fact, there are some basic math model for that event streams. 3 of these most classic models are Poisson process, non-homogeneous Poisson process, and Hawks process. We know that Poisson process assumes that events occur independently of each other, and the non-homogeneous Poisson process, they assume that the probability of an event happening at the time t may vary with the t, but in fact, it is still independent of each other. And the Hawks process suppose that the past event can temporarily raise the probability of future events, assuming that such excitation is positive, active over the past events, and will decaying with the time. But this basic math models have some constraints. First, it will be violated if one event inhibits another rather than exciting it, such as if you buy a cookie and this event will inhibit you to buy another cake. And second, it will be violated when the combined effect of the past events is not additive, such as that the new advertisement sometimes does not increase purchase rate as much as the early advertisement did, and may even drive customers away. And the second, it will be violated when a past event has a delayed effect. Sometimes the effect of an event will not be present at a new event immediately, but the basic point process cannot deal with this condition. So this paper, in this paper, in order to deal with these problems, they introduced a new model called neural point process model. In order to introduce this model, we will first reveal the basic process, Hawk's process. Hawk's process is a self-exciting multivariate point process. In order to understand the Hawk's process, we first introduce the non-homogeneous multivariate Poisson process. We can see this function. It is a basic model of event stream. It assumes that an event of type K occurs at time t with and the value lambda t can be regarded as a rate per unit time, just like the parameters lambda in the traditional Hawk's process. And lambda k is known as the intensity function. The total intensity of all these event types is given by the first equation. It just sums them up. And a more complex model is the self-exciting multivariate point process, also called the Hawk's process. This is the second equation, which supposes that past event can temporarily raise the probability of future events, assuming that such excitation is positive, additive over the past event and decaying with time. The mu k in this equation is the base intensity of event type k, and this alpha jk is the degree to which an event of type j exceeds type k, and this delta jk, delta khk is the decay rate of the excitation. So for the traditional Hawk's model, the positive constraints in the Hawk's process limit its expressivity. First, the interaction parameters alpha jk fail to capture the inhibit effects. It just can express the positive effect. This will reduce the intensity, and but the inhibit effects will reduce the intensity of the future events. So, and the other problem is that the past events must have independent additive influence on the new events. But in fact, some sequence in our daily life cannot satisfy this. So in this new model, they removed these two constraints just as before. Each event type K has a time varying intensity lambda kt, which jumped discontinuously at each time event, and then drops continuously toward the baseline intensity. In the new process, however, this dynamics are controlled by a hidden seed vector, which in turn depends on a vector of memory cells in continuously time LSTM. So first is to relax the positive constraint on alpha jk and mu k. We can see that in the traditional Hawk's process, this lambda k and this lambda k must be positive. But in fact, if we remove these constraints, we need a function to transfer this lambda k to a positive value. So the fx, in fact, it's a soft plus function. It's used to transfer the lambda k to a positive value. This is the first constraint. The second constraint is that second constraint is that the past events have independently actively influenced on lambda kt, so that they choose the RNN architecture. And this model, in fact, is very similar to the discrete time LSTM. The difference is that each memory cell C in this model will decay its summary data and finally reach some steady values. The HT is very similar to the LSTM model, just the normal language model, which summarizes the past event sequence K1 to Ki. But in here, the K is the type of the events, not the word vectors. So because of the decays, this model will not only reflect the types, but also reflect the time. We can see this formulas. Other than depending on decayed values, the updated formulas will resemble to the discrete time cases. They look at these formulas, we can see that there is mainly two big differences from the LSTM. The first is that LSTM updates depends on the previous hidden state. In this model, the updates depend on its value HTI at time TI. After it has decayed for a period from the last time to this time. And the second, we can see that the equation 6b, 6c, these two new equations. They define how in future the element of CT will continue to decay at a different rate, of course, from C towards target. Toward target C is a steady rate. So their main motivation in this is that making a model that can capture effects that the Hawkes process misses. LSTM, we can see this finger. This finger is the whole structure of the whole model. LSTM reads the sequence of past events to arrive at a hidden state. That state determines the future intensity of two types of events. The intensity functions are the solid lines determined by the most recent LSTM state with dashed lines showing that the steady state lambda that they should eventually approach. In this example, events of type 1 excited type 1 but inhibit type 2. So from this finger, we can see that the way that so from this finger, we can see that the type event of type 1 will excite the type 1 but inhibit the type 2, and the type 2 excites itself and excites or inhibits type 1 according to whether the count of type 2 is odd or even. And then we will talk about the log likelihood part. The log likelihood is very simple. It's just the sum of the log intensity of the events that happened at the time they happened, minus an integral of the total intensity over the observation interval 0 to t. And then we will talk the model training. They use the single layer LSTM in model and empirically find the model performance in robust to a set of hyperparameters. Second, they use the Adam algorithm as their optimization algorithm with the default settings. Then we will talk about the experiments. This experiment was published on the real-world media dataset. First, the first finger is the meme track. It contains timestamps instead of meme used in articles and posts from 1.5 million different blogs and news sites. The event type corresponds to the different websites, and the K equals 5,000. And the next finger shows the retrieve data set, include about 16,100 retrieve sequence, each corresponding to some original tweets. They divide the events into K equals 3 types, retrieved by small, medium, and large users. And we can see that the NFM MPP is the neural host process model, and the DSM MPP is the model just to relax the first constraint. SEMPP is a host process model. The performance of the neural model is significantly better than the DSM MPP model and the host process. And the next experiment is to comparing the holdout logarithmic fold of the two models. We can see that all these points fall to the right of the y equals x. Since NSMPP, that means the neural host process is constantly more productive than the host process, and we can see the red finger should also show that the NSMPP is better than the DSMMPP, which shows that if we relax the two constraints, it will have better performance than we just relax the first constraint. The final part is the conclusion. In this paper, they presented two extensions to the multivariate host process, a popular generative model of stream of time-stamped events. They relaxed two constraints we mentioned before. First is that past events may not either exit or inhibit future events. They do so by sequentially updating the state of novel continuous time with RTM effect. Second is that host sums the time decaying influence of the past events. They instead sum up the time decaying influence on the LSTM nodes, which will help the model can predict the future events, which is not just an additive pattern from the past sequence. Thank you.